For more than a century, humanity has built power plants on Earth. We drill for fuel, mine resources, construct transmission networks, and distribute electricity across vast distances. Every modern city depends on an enormous web of infrastructure hidden beneath our daily lives. But what if the next great power plant was not built on Earth at all? What if it was built in orbit, continuously collecting sunlight and transmitting energy back to the planet below? At first glance, space-based solar power sounds like science fiction. A giant solar array floating above Earth, beaming energy to the surface without wires, seems more like a futuristic concept than an engineering reality. Yet behind this vision lies a collection of technologies that already exist in various forms today. Solar arrays power satellites. Robotic systems assemble structures in space. Wireless energy transmission has been demonstrated for decades. Advanced control systems guide spacecraft with astonishing precision. The real challenge is not a single technology. The challenge is integrating thousands of technologies into one enormous system. Launch infrastructure, manufacturing facilities, robotic assembly platforms, power electronics, communication systems, beam control networks, receiving stations, and grid infrastructure must all operate together seamlessly. What appears to be a single satellite is actually one of the most complex infrastructure projects ever imagined. To understand how power could come from space, we must first uncover the hidden industrial systems that make such a vision possible. Long before electricity is generated in orbit, the project begins on Earth. Every component of a space-based solar power system must first be designed, manufactured, tested, transported, and launched. Thousands of companies may contribute specialized components ranging from solar cells and structural materials to electronics, propulsion systems, communication equipment, and software. Factories produce precision hardware capable of surviving launch stresses and operating in the harsh environment of space. Engineers conduct extensive quality assurance testing because failure in orbit can be extremely expensive. Massive launch facilities prepare payloads for deployment. Transportation networks move equipment between suppliers, assembly plants, and launch sites. Mission control centers coordinate operations from initial construction through long-term maintenance. The launch vehicle itself becomes part of the infrastructure story. Rockets are not simply transportation systems. They are supply chains connecting Earth to orbit. Every kilogram delivered to space requires fuel, logistics, planning, manufacturing, and operational expertise. As the size of the orbital power station grows, launch operations become increasingly important. Viewed from this perspective, space-based solar power is not merely an energy project. It is a global industrial ecosystem. Manufacturers, logistics providers, launch companies, software developers, aerospace engineers, and infrastructure specialists all contribute to the final system. Before the first solar panel ever reaches orbit, an enormous network of hidden systems is already working together on Earth. Unlike traditional satellites, a space-based solar power station may span kilometers in length. Structures of this scale cannot realistically be launched as a single unit. Instead, they must be assembled piece by piece in orbit. This transforms space from a destination into a construction site. Cargo spacecraft continuously deliver modules, structural components, solar panels, power systems, and robotic equipment. Autonomous assembly systems connect these modules together with extraordinary precision. Robotic arms position trusses, align structural elements, install power systems, and perform maintenance activities. Advanced sensors ensure that every connection meets strict engineering requirements. Modular construction offers important advantages. New sections can be added over time, allowing the power station to expand as demand increases. Damaged components can potentially be replaced without dismantling the entire structure. Upgrades can be integrated as technologies improve. Building infrastructure in orbit introduces unique challenges. There is no conventional construction equipment, no atmosphere, and no easy access to replacement parts. Every component must function reliably in microgravity while enduring temperature extremes, radiation exposure, and decades of continuous operation. The result is something humanity has never attempted at this scale: an orbital industrial platform capable of constructing and maintaining one of the largest engineered structures ever built. Space-based solar power may ultimately depend as much on orbital manufacturing and robotic construction as it does on solar technology itself. The primary advantage of space-based solar power is simple yet powerful. Sunlight in space is abundant, continuous, and largely uninterrupted. On Earth, solar panels must contend with clouds, weather systems, seasonal changes, atmospheric absorption, and nighttime darkness. In orbit, many of those limitations disappear. Massive photovoltaic arrays capture solar energy with exceptional consistency. High-efficiency solar cells convert sunlight into electricity, while advanced collection systems gather and route power throughout the structure. High-voltage DC buses transport energy from thousands of interconnected panels towards centralized power management systems. Thermal management becomes critical. Even highly efficient solar cells generate heat. Without proper cooling, performance declines and equipment reliability suffers. Radiators and thermal control systems continuously remove excess heat while maintaining optimal operating temperatures. The scale of energy collection is enormous. A fully developed orbital solar power station could potentially collect gigawatts of energy continuously, producing electricity day and night regardless of weather conditions below. Unlike terrestrial solar farms, energy generation does not stop when the sun sets. This continuous collection capability is one of the defining characteristics of the concept. The goal is not simply to build another solar installation. The goal is to create a new category of energy infrastructure capable of delivering reliable power around the clock. Every solar panel becomes part of a larger system designed to harvest one of the most abundant resources in the solar system: sunlight itself. Collecting solar energy is only the first step. The electricity generated by the solar arrays must be processed, regulated, and transformed into a form suitable for long-distance wireless transmission. This is where the orbital power station begins to resemble a sophisticated power plant. Electricity flows through high-voltage DC collection networks into advanced power electronic systems. These systems regulate voltage, manage current flow, stabilize power quality, and coordinate energy distribution throughout the station. Buffering systems help smooth fluctuations and ensure continuous operation. Next comes one of the most important functions in the entire architecture: energy conversion. Specialized microwave generation systems transform electrical energy into radio frequency energy. This conversion process must operate at extremely high efficiency because losses become significant at gigawatt scales. Thermal management systems continuously remove waste heat generated during conversion. Without effective cooling, equipment temperatures could quickly exceed operational limits. Reliability and efficiency therefore become inseparable engineering objectives. The power conversion section effectively serves as the heart of the orbital power station. It transforms raw electrical energy collected from sunlight into a precisely controlled energy stream capable of crossing the distance between orbit and Earth. Every component inside this section contributes to a larger objective. Solar energy collected hundreds of kilometers above Earth must eventually become usable electricity on the ground. The conversion process bridges that gap and prepares the energy for its next stage: transmission. Delivering gigawatts of energy safely requires extraordinary precision. A space-based solar power station cannot simply broadcast energy in every direction. Instead, it must shape, control, and continuously guide the beam toward a designated receiving station on Earth. This capability is achieved through phased array antenna technology. Thousands or potentially millions of synchronized antenna elements operate together as a single coordinated system. By carefully controlling the phase and timing of signals, the beam can be directed with remarkable accuracy. Artificial intelligence and advanced control systems continuously monitor performance. Satellite movement, orbital dynamics, Earth's rotation, atmospheric conditions, and environmental changes all influence beam alignment. Real-time adjustments ensure that energy remains focused on the intended target. Redundancy is essential. Multiple layers of control systems provide backup capabilities and improve reliability. Safety systems monitor beam characteristics and automatically respond if operating conditions deviate from acceptable limits. The engineering challenge is enormous. The system must deliver energy across vast distances while maintaining precise control every second of every day. Even minor alignment errors can reduce efficiency or affect performance. What makes this remarkable is that the beam control system effectively becomes a navigation system for energy itself. Instead of guiding a spacecraft through space, it guides power from orbit to Earth. The success of the entire concept depends on the ability to maintain this precision continuously and safely over decades of operation. For more than a century, electricity has been transported primarily through physical wires. Space-based solar power introduces a radically different approach. Instead of transmission lines stretching across landscapes, energy travels wirelessly through space and the atmosphere. Once generated and shaped by the orbital power station, microwave energy is transmitted toward Earth as a focused beam. Advanced beamforming systems maximize efficiency while maintaining stability throughout the transmission process. Continuous monitoring ensures safe and reliable operation. Wireless transmission offers unique possibilities. Energy can potentially be delivered across great distances without constructing vast networks of transmission towers. Remote regions, islands, isolated industrial facilities, and developing areas could gain access to reliable electricity through entirely new infrastructure pathways. The concept relies on decades of research into microwave transmission and antenna technology. While significant engineering challenges remain, the underlying principles are well understood. The goal is to deliver large quantities of energy efficiently while minimizing losses and maintaining strict safety standards. The beam itself becomes part of a larger energy corridor, linking orbital infrastructure to ground-based systems. Unlike conventional power lines, this corridor exists through controlled electromagnetic transmission. This stage represents one of the most revolutionary aspects of the entire concept. Electricity generated in space travels across hundreds of kilometers without physical conductors. If successful, it could redefine how humanity thinks about energy delivery and long-distance power infrastructure. At this point, the individual technologies begin to merge into a single integrated system. Solar arrays collect sunlight. Power electronics regulate electricity. Conversion systems generate microwave energy. Phased arrays direct the beam. Receiving stations capture the transmitted energy. Grid infrastructure distributes electricity to consumers. None of these systems operate independently. Each depends on the performance of every other subsystem. A disruption in solar collection affects power generation. Conversion efficiency influences transmission performance. Beam accuracy impacts receiving efficiency. Grid integration determines how effectively electricity reaches end users. This interconnected architecture transforms separate technologies into a unified energy ecosystem. The result is not merely a satellite, a solar farm, or a transmission system. It is an entirely new category of infrastructure operating across Earth and space simultaneously. The scale of integration required is extraordinary. Aerospace engineering, power generation, telecommunications, robotics, automation, software systems, manufacturing, and utility infrastructure all converge within a single project. This is why space-based solar power attracts so much attention from researchers and policymakers. Its significance extends beyond renewable energy. It represents the possibility of creating a continuously operating, globally connected energy platform. The concept challenges traditional assumptions about where energy infrastructure must exist. Instead of building power plants solely on Earth, humanity could someday expand critical infrastructure into orbit, opening entirely new possibilities for energy generation and distribution. One of the strongest arguments for space-based solar power is reliability. Traditional renewable energy systems often depend on local weather conditions, seasonal patterns, and geographic location. In contrast, orbital solar power systems can access sunlight far more consistently. Continuous energy generation creates opportunities for improved grid stability and long-duration energy supply. Regions with limited renewable resources could potentially benefit from energy delivered from space. Remote communities, industrial facilities, transportation systems, and critical infrastructure could gain access to dependable electricity. The environmental benefits are equally important. The system generates electricity without direct combustion and without consuming fuel during operation. Energy is produced through continuous solar collection rather than ongoing extraction of natural resources. Scalability is another attractive characteristic. Additional orbital platforms could increase generating capacity over time. As launch costs decline and space infrastructure expands, larger systems become increasingly feasible. Perhaps most importantly, the concept expands humanity's energy options. Rather than replacing existing technologies, space-based solar power could complement terrestrial renewables, energy storage systems, advanced nuclear technologies, and future grid architectures. The objective is not simply more electricity. The objective is greater resilience, flexibility, and sustainability. By extending energy infrastructure beyond Earth's surface, humanity may gain access to a new source of continuous power, capable of supporting future economic growth and technological development. Today, space-based solar power remains largely a future-oriented vision. Yet many of the technologies required to make it possible are advancing rapidly. Launch costs continue to decline. Robotic systems are becoming more capable. Solar technologies are improving. Artificial intelligence is transforming automation and control. Future orbital power stations could operate as part of a larger network supporting global electricity demand. Multiple platforms may serve different regions while providing redundancy and operational flexibility. Space infrastructure could evolve from isolated satellites into interconnected industrial ecosystems. Governments, research organizations, universities, utilities, and private companies are actively studying aspects of the concept. Pilot projects, technology demonstrations, and research programs continue to explore technical feasibility and economic viability. Significant challenges remain. Construction costs, operational complexity, maintenance requirements, regulatory frameworks, and large-scale deployment strategies must all be addressed. Yet many transformative technologies faced similar skepticism during their early development. History repeatedly demonstrates that ambitious infrastructure projects often begin as seemingly impossible ideas. Railways, aviation networks, telecommunication systems, and global internet infrastructure all evolved through decades of engineering progress. Space-based solar power may follow a similar path. Whether deployment occurs in 10 years or 50 years, the concept provides a glimpse into a future where energy infrastructure extends beyond Earth itself and becomes part of humanity's broader presence in space. The story of space-based solar power is ultimately not about a satellite. It is about systems. Hidden beneath every technological breakthrough lies a vast network of engineering, manufacturing, logistics, automation, infrastructure, and industrial expertise. Those systems rarely make headlines, yet they are the foundation upon which modern civilization is built. The same principle applies across the energy industry. Hydrogen production facilities depend on water treatment systems, compressors, storage tanks, pipelines, and fueling infrastructure. Data centers rely on power systems, cooling networks, backup generation, and communications infrastructure. Industrial facilities operate through thousands of interconnected components working together behind the scenes. Space-based solar power simply expands this idea to a planetary scale. It combines launch systems, orbital construction, solar collection, wireless transmission, receiving stations, and grid infrastructure into one integrated network. Understanding these systems helps us understand how future energy infrastructure may evolve. At ReneEnergy, our mission is to uncover these hidden systems and explain how they work. Through H2 Hub and ReneEnergy, we explore hydrogen technologies, industrial infrastructure, clean energy systems, water treatment technologies, fuel cells, compression systems, storage solutions, and the engineering realities shaping the future. Because the future is not built by a single machine, it is built by thousands of interconnected systems working together. And when you begin to see those systems, you begin to understand how civilization itself works. This is H2 Hub by ReneEnergy, exploring the engineering behind energy, hydrogen, infrastructure, and industrial transformation. Because the systems behind civilization are the systems building the future.